We can also define a log normal tree. And here you can see that the drift term, compared to the binomial tree we worked with in the last module, we have an extra adjustment to the drift. The extra adjustment to the drift reduces it by a half the variance. And notice, because that sigma squared is being multiplied by h, we're reducing the period return by 1/2 the period variance. This adjustment will be seen later in the chapters on the Black-Scholes model and Ito processes. We'll be seeing that term. Once again, it looks as if this would be quite a significant adjustment. We're adjusting the drift, but interestingly, remember, by changing U and D, we change P star. If we change P star, we change option prices, and when we which changes the exercise value and the option prices. And in the limit, as h goes to 0, they all converge to the same price. It's quite remarkable, perhaps, but when you do the math correctly, you'll find that it's true. So this binomial model is a form of a random walk. We can see that we're going to make some assumptions, however, and the random walk is in the return. Again, just to make that clear, in all of these, we have a random walk. You see a plus and a -1 in the return. If we go back to the Cox-Ross-Rubinstein model, the random walk is evidenced by the +1 up here and the -1. And similarly, in the very first tree we looked at, we saw the plus or -1 in front of the sigma term. So there's always a random walk embedded in these binomial trees, and they're usually or typically embedded in the exponent, the return, that one assumes in this tree. But we have to assume volatility is constant. It's an important assumption that sigma is constant, and that may or may not be appropriate depending on the model. For example, if we were modeling bond prices, we couldn't possibly use this method for an option on a 5-year bond, because we know that bond price volatility diminishes as the bond approaches maturity. So we couldn't possibly have sigma constant. But sigma being constant is not a bad assumption for many other forms of securities. We also assume that we can't have large, discrete stock price movements. We're basically modeling that the change in stock prices is related to the time interval, that you can't have, in a very short period of time, a very big move in prices. There are models that generalize in this direction, but this model assumes that stock price changes, are governed by the period of time, and the returns that are possible and the probabilities of those returns depends on how long the period is. Finally, we assume that the returns are independent, or at least we assume that they're uncorrelated period to period. And remember, the correlation, the lack of correlation, was important because it told us that's where the square root rule came from, that the variance over a long period is a sum of the sub-period variances. And that's what gives us that the variance proportional to time and volatility, standard deviation, is proportional to square root of time. All of these assumptions appear to be violated somewhat in the data. If you study stock price series, you'll find that different series provide challenges to these. The methodologies that we study in this book, however, are still quite popular in the market, provide good tools for the problems at hand, and people are well versed with knowing how to sometimes, in an ad hoc basis, make adjustments to the prices from these models to reflect some of the model's shortcomings.